who is my collaborator before, and recently, and the talk of Pierre, who is Charles' collaborator. So there was like four different talks on the same topic. So I hope I'll bring actually some new aspect here. Okay, so essentially, okay, so let me minimize this. Okay, so essentially, this theory is called the wave turbulence theory because it's based on the wave systems, like essentially dispersive systems, and it's also called the weak turbulence theory because it's based on the setting where you have a weak nonlinearity, which I'll explain later what that is. Sorry. So this was like dating back to the 20th century, and there are different people deriving like heuristic models. Peels in 1928, I mean, some wrote in 1929, I'm not sure, and Hasselmann in 1960s, and then the people Zakharov and collaborators has made these contributions, made this into a significant subject. And it's essentially this concerns the derivation of some kind of effective equation for some many mode wave systems in a pseudo limit. Okay, so I'll explain what that is. And this is for like comparison for like high level like an analogy, you can think of the derivation of Boltzmann's kinetic theory that is from the system of many particles, and this was like in the case in the case corresponding to what I consider now is derived by rigorously derived by the work of Lanford in 1975. And these roughly, like broadly speaking, this fall under the category of the Hilbert-6 problem, which is a rigorous justification of the laws of statistical physics. Okay, I will make further comparisons between these two problems, like high-level comparisons, like as we go on. Actually, there will be some kind of high-level analogies here. Okay, and in this talk, we're going to focus on the model equation, which is a cubic nonlinear Schrodinger equation, which is really the most in terms of dispersive equations, is the most essentially the most simplest model. However, we remark that our method is actually applicable for many other equations, including quasilinear equations such as water wave. Essentially, my belief is that if we restrict to semilinear equations, then our method is not only applicable, it should be able to lead us to the optimal timescale as we'll describe later in this case. And in the case of quasilinear equations, we'll get perhaps some somewhat weaker result, but we'll still be able to apply these methods. Okay, so we'll talk about this later. Okay, and the model we are considering here is a cubic nonlinear Schrodinger equation, so which is this one. So we're considering this on a large box, which is a rescaled unit torus. We think the unit torus as being the 0, 1 to the d, and then the rescaled torus will be the 0, L to d, or a torus of size L. So this, yeah, and we all made the 2 pi factor. So by the way, there's a joke that that one of my friends, he when he was giving a talk related for analysis, he usually he said like something that in the beginning of talk was saying that in this talk we're assuming that 1 equals 2 pi, but then I was thinking that 1 equals 2 pi actually implies anything. Okay, that was a joke. So so this is the nonlinear Schrodinger equation on large box. We're considering this slightly twisted Laplacian, which has these coefficients beta 1 to beta d. So we're considering this because we also want to consider the standard nonlinear Schrodinger equation on the general rectangular torus, like instead of TL to d, instead of ZL to d. We're considering, say, like 0 from 0 to beta 1L times 0 to beta 2L times 0 to beta DL. In this case, if you do a change of variable, you can easily reduce to the equation on the standard torus, but with this twisted Laplacian. Okay. And so yeah, and we'll assume dimension is at least 2, and actually in most interesting case the dimension is at least 3. Okay, so the solution will essentially, we think our solution has first support in k less than 1. So if you remember that okay, I forgot to write, but the x variable is in the big box, and the Fourier variable, the dual Fourier variable, is in the fine like mesh of is in a very fine mesh of mesh size 1 over L, because the dual of this large box, when L goes to infinity, this domain like approaches the whole of RD, and this mesh, like this fine mesh, also approaches whole of RD. Okay, so I forgot to write. So this the dual of this TLD is called the ZL to D, which is like a Z to D, but with mesh size 1 over L. So when L goes to infinity, this becomes the continuous continuous continuum. Okay. And so here we can, like, if you want, we can do a rescaling like of the equation, that we rescale it so that the initial data lives on the standard unit torus, and that is okay. But then the initial data will be supported in the frequencies k less than L instead of k less than 1 in the original picture. And we have a standard torus with initial data having essentially support of in a ball of radius L. Okay, so this is also something that has been considered, like this is something that if you consider like a nonlinear Schrodinger equation with the on the standard unit torus with the with the initial data supporting on the frequencies of size L, and then this is essentially a typical case we are considering here. Here we're considering the rescaled version of this. You can view it from different aspects. Okay, and then we're considering this twisted Laplacian. So actually, in one of our results, this beta will be arbitrary, and one of our results work for arbitrary choice of beta, and for another result, we actually need the beta to be like satisfying genericity condition that, namely, we are going to exclude like a Lebesgue measure 0 set from the set of parameters of beta, and in this case, and under this genericity assumption, we're going to get like a much better like result in terms of time scale we're getting. Okay, so again, like, so by the way, so if anyone has questions, like, are they typing in the chat or what? Sorry, let me wait. Okay, but I mean, okay, so I think I'll just go on. So I guess if anyone has questions, they can type in the chat. I'll look at the chats kind of regularly, let's say. Okay, so the model, in the setting here, instead of considering individual equation, we're considering this so-called ensemble, namely the family equation that obeys a specific law of distribution. And of course, this also, if you compare with the case of kinetic theory, it's also consistent with the idea of kinetic theory, where instead of like individual particles, we're considering the interaction of like many particles, but we're concerning, we're interested in the like distribution in terms of the position and velocity of the particles. And here it's kind of the same, like instead of like these single individual solutions to this equation, we're considering this all the set of solution as a large ensemble, and then we're really interested in this law, and in the so-called average among these ensembles. Okay, and the law we are considering is a usual thing that's essentially have been standard for the past few decades. We're considering these we're considering this Gaussian distribution, or like a distributions of slightly different form. But the point here is that we're considering the case where all the Fourier coefficients are independent and identically, essentially identically distributed. Okay, so this corresponding to this this random data problem, and actually the random data problem, I'll mention a little bit about the general random data problem, and that's closely related to the theorem, to the problem we're talking about here. So you can see this this random data problem where the initial data is so this is like a normalization constant, and we have this Fourier coefficients. Well, this Fourier coefficients has some particular size. Well, this essentially you can think of as this initial, n initial is a Schwarz function with essentially you can view it as a like a restriction to this k to k less than or equal to 1, and then you have this this e to k omega, which is the main thing. E to k is okay, so this e to k is the identically distributed independent random variables that satisfy specific law of distribution. Okay, so here ZL to D is the dual of the large torus, so it's a measure of size 1 over L that goes to 0 when L goes to infinity. Okay, and this ID variable is on the next slide. So this E to K are identically independent, identically distributed complex random variables that we only assume that rotation is symmetric and have exponential tails. Actually, we can our result works for a lot of different laws, but the point is that this E to K should be independent. Okay, so there are two specific cases of interest: the Gaussian setting where the ensemble is a Gaussian law, where E to K is a Gaussian variable, or we can consider the random phase setting, which is kind of slightly more natural because here in this case each E to K is uniformly distributed on the unit circle of C. So essentially, in the random phase setting, this is the the norm. This square root n initial of K is a norm of the Fourier modes, and E to K is a random phase of the Fourier modes. Okay, so this is a setting, and actually essentially, if you consider rescaling like back to the unit torus, then you're considering the random initial data where the Fourier the Fourier modes are supported in the ball of of size L, and these Fourier modes are essentially like independent, uniformly distributed, and independent. Okay, so this is kind of a very generic. If you think of what would be a generic initial data for data supported in the ball of size K, and that will essentially be the generic data. So this is kind of, you can think of this our result as an analysis of this nonlinear Schrodinger equation with generic generic initial data. And here is just rescaled version of this. Okay, so what happens if you have this generic data? So one thing, one easy consequence is that you can have this constraint inequality for this random initial data. A constraint inequality essentially is saying that if you have a random like a function on the torus that's whose Fourier modes are independent, then the L infinity norm of this random function is almost comparable to L2 norm of this function, like regardless of like what frequency you are. This gains actually you a lot of derivative compared to the Sobolev embedding. Okay, so if you apply this constraint inequality, what happens is that you can get this like in the rescale setting, the L2 norm of F is comparable to 1, so the L infinity norm of F is compared to this norm L to the L infinity norm is comparable to with this L to minus D over 2, which gains you a lot. And then the point here is that if you assume that this randomness can be propagated, of course, this is a most important thing, because if you start with like random initial data, then as long as your time is positive, this independence between the Fourier mode will no longer be true, and you need to find a way to capture this propagation randomness, and this actually the main major part of our work to capture the propagation of randomness under the nonlinear Schrodinger flow. Okay, so if you assume this can be propagated, then you can essentially consider the strength, so-called strength of nonlinearity, which is essentially the the ratio between nonlinear term and the linear term, which is essentially like lambda square times mod u square. If you remember that in the equation we're having this lambda square here, like on the nonlinearity. So this is like lambda square, lambda square times mod u square. You can view it as the size of nonlinearity. And then in this case, the strength of nonlinearity would be like lambda square times L minus D. Okay, so this value lambda square L minus D is actually a critical value like in our problem, and we'll call it alpha. Okay, so the setting we're considering is the so-called large box and weak nonlinearity limit. Well, large box means L goes to infinity, and weak nonlinearity means that that alpha goes to 0. Okay, so so this is the setting we're considering, and find what is the quantity we're looking at. So if you start with this random initial data, and you can consider this data in this particular ensemble, and then we're evolving this ensemble according to the nonlinear Schrodinger equation, and then like later on we're having completely like the different distribution, and we're not in the so-called stationary case where we have a formed invariant measure or such. We're not. We're having this non-equilibrium state. And then the thing we're studying is the so-called ensemble averages, the expectation of the size of the Fourier mode squared. So essentially, you can think these are the quantities that we can actually observe. These are the statistical averages, statistical quantities that we can actually observe. Essentially, you can view it like we start with some particular values of Fourier modes, and then we randomize this phase. We consider this corresponding ensemble, and then we let ensemble evolve. And in the end, at some later time, we're recovering a different ensemble, and then we're trying to recover essentially the expected size of the average, the statistical average of these Fourier modes at this new time. And our question is we start with some value of statistical average, and we end up with some other statistical averages at later times. The question is how does this statistical average, how does it evolve? Okay, so because this one is the kind of the actual thing that we can observe in a statistical setting. So of course the question is if you think the underlying system is a nonlinear Schrodinger equation, then how does these observables, how do they evolve? They should say some kind of effective equation, and what that is, and how do we derive it? Okay, so that's the kind of the question we're interested in. From the point of view of statistical physics, is quite natural, and also from the point of view of random data theory for nonlinear dispersive equation, is also quite natural because what we're interested in is also in the evolution of these Fourier modes, of these random Fourier modes. Okay, so let's continue with this equation, this effective equation in we call the wave kinetic equation. Okay, so here's the calculation have been done by physicists. So as I mentioned, these people from the 20th century, they have done a lot of heuristic calculations, including Zakharov, Nazarenko, and the collaborators. And they have formally derived an equation in that they expect these ensemble averages to satisfy in the limit. Of course, after rescaling time, that the equation they write down is essentially this equation called the wave kinetic equation. So here, this n is essentially is linked to the n initial which is the initial ensemble average of the Fourier modes. Okay, so this d tau of n, where tau is rescale time of t, d tau of n at tau and k is equal to the integral of kj. Kj is in Rd, where you have this, let's satisfy these two resonance equations. So k minus k1 plus k2 minus k3 equals 0. So this kind of corresponds to Kirchhoff's law. And mod k square minus mod k1 square plus mod k2 square minus mod k2 square plus mod k3 square equals 0. So that's what type of minus k2 mod k square plus k3 square equals 0, and this is a resonance condition. And then we have this n tau k, n tau k1, n tau k2, n tau k3 times this 1 over n tau k1 minus 1 over n tau k2 plus 1 over n tau k3 minus 1 over n tau k. So this is like a combination of the cubic products of these three of these factors. And then the d tau of n is equal to the integral of this. Okay, so you can view it as the right hand side as collision kind of nonlinearity, where the integral is taking over all these k on k2 k3 that satisfy these resonance conditions. Okay, so here this mod k beta is the norm quadratic form associated with the twisted Laplacian. So later on we'll just view it as the same as mod k. Okay, so there is a huge derivation of this, which we'll mention a little bit in the later proof, but this is essentially the thing that is derived by physicists, like from looking at the first order terms of the expansion of the solution, and then you do the expectations, and you end up with this nice equation. Actually, this equation has a nice behavior, and recently there works around like just proving the local and global oppositeness of this equation. But of course, in this work, we only cared about this equation for short times, and then we're just interested in the derivation of this equation. Okay, so this is a conjecture. This is a conjecture that's essentially comes from work of physicists. So we can just consider this Schrodinger equation with this random initial data. Okay, so it's this, let's consider, say, the random phase. We define so recall that alpha is the size of the nonlinearity. We define this T kinetic, which we call the kinetic time scale, to be alpha minus 2, and we'll see how this time scale emerges like later on in the heuristic argument, which is equal to lambda to the 4 L minus 2D. Define this to a kinetic time scale. Then, okay, so actually we should say here under certain restrictions for between alpha and L. Okay, so this restriction will make precise later. Under these restrictions, for t between 0 and tau 0 times the kinetic time, okay, where tau 0 is a fixed constant independent of L and alpha, we would have this ensemble average, this statistical average, would equal to the n of this time t over kinetic time at k plus a remainder term O of 1, where this n is exactly a solution to the wave kinetic equation.
Yu Deng.
Yes. Yeah, okay, yeah, I see. So there is there are books on wave turbulence, I think by Nazarenko, that has a discussion of this wave kinetic equation not only for Schrodinger but for all different kind of equation. I think it's a book of Nazarenko, and it's called either, I think it's called wave. I think the title contains the word wave turbulence or weak turbulence or something like that. Okay, and yeah, so and there are, of course, there are papers like and there are the works I mentioned before, but I think that book has everything. Okay, so where this n is a solution to the wave kinetic equation with initial data, which is the I think n0k is the I think it's not this one. It's the n initial n in of k, which is the one that appears in which is this one. So which is this one. Okay, so with the n n0 initial data being the initial data we're given, and this O1 is a quantity that goes to 0 uniformly in T and K under suitable limits along which L goes to infinity and alpha goes to 0. Okay, so this is a big conjecture in this theory. So this conjecture is essentially corresponds to establishing the effective dynamics of this wave kinetic equation up to Rescale time tau equals tau 0, where we expect tau 0 to be independent of this L, independent in the limit. Okay, so in this case, we're saying that we can justify the wave kinetic equation up to this time tau 0 times the kinetic timescale. Okay, so as of now, this conjecture is still open, and it's still open even for like very small tau 0, as long as we require tau 0 to be independent of L. Actually, in all the existing results, this tau 0 actually depends, in all the existing results, tau 0 has to depend on L and alpha, and actually in the limits L goes to infinity and alpha goes to 0, this tau 0 actually goes to 0. And actually, like, of course, the goal is to establish this conjecture for tau 0 independent of L, and so that we can really justify the dynamics of the wave kinetic equation, like for some positive time. Like if tau 0 goes to 0 together with L, then in the limit we're still kind of considering the wave kinetic equation, like up to time 0, because the tau 0 is this time. If tau 0 goes to 0 and as L goes to infinity, this would be corresponding to like infinitesimally small time for wave kinetic equation, but the goal is to get to like some positive time for the wave kinetic equation for tau 0 independent of L. Of course, that would be a major goal of this research. Of course, the ultimate goal would be to justify this for arbitrary large L, but that seems kind of pretty far away. Even the result of small L seems pretty far away as of now. Okay, so there's a question I see. So is there a conjecture for this without taking expectation? I mean, without taking expectation, then I mean this will be like a statistical. This will be like a random variable. And how do you quantify a random variable? You can. So I think our result actually implies that that if you do not take expectation, like up to the time we are having right now, up to the time we're obtaining this random variable, they have some explicit expression plus some error term, which is a very small size. But this expression is kind of very complicated. I mean, it's good to have, but it may not be very nice to explicitly write out. So there is another question in the chat. Yeah, distribution essentially the main, like the leading like component are still the linear Gaussians, and then they have some high order Gaussians which whose size is smaller than the main term, but it's perturbed this distribution a little bit perhaps, but essentially that distribution is still satisfied like exponential tail, and these kind of things they are still fine. So, and of course all the modes will not be independent, but if you consider the correlation of the modes, they still like they still kind of they still kind of decays like L goes with things like approximately. So yeah, so the correlation between different modes and also correlation between different times, but that's a thing that should also decay like suitably like in the limit. Okay, so okay, and yeah, so yeah, and also the work of Buckmaster, Zaher Hani, Shadha, they have some deterministic result that can reach like a shorter time scale. So if I have time, I'll also mention this later. But if I have time, okay. So then this conjecture may also depend on the way in which L goes to infinity and alpha goes to 0 so there is possibly like a favorable like scaling between L and alpha that make this work or not, but we'll mention this. We'll talk about this later when we state our theorem. Okay, so the previous results in this direction, there have been results like for simplified or related models, like for example, there is work of Erdos and Yang, which established some version of this result for linear Schrodinger equation with the potential. And actually they were considering this random data problem for linear Schrodinger equation with potential. And then they, with Sam Hoffer, they later extended this to longer time scales. And in the case of linear equation, they were able not only to reach the kinetic time scale, they were also actually extending to longer time scale, which is kind of not expected in the nonlinear case. And then there is a work of Lucarini and Sprung, and they were considering a slightly different set. They were considering nonlinear Schrodinger equation, but on the lattice, and also they're considering the dynamics of a Gibbs measure, which is equilibrium dynamics in the statistical sense. But here we're considering non-equilibrium dynamics because we don't have any invariant measure here. Okay, so for conjecture itself, for this particular problem for the Schrodinger equation, so there was this recent result of Buckmaster, Germain, Hani, and Chatat, who was able to justify this wave-Kinetic equation up to this time t0, which is essentially, I mean, they have a complicated expression, but here I'm just writing this as L to minus 3 times kinetic time. It's actually like L to minus 3.01 or something in the 3 dimension for certain ranges of this strength nonlinearity alpha in terms of L. Okay, so this is like from the point of view of establishing conjecture, this is maybe not a very optimal thing, because this kind of, you see this, you're having like L to minus 3 like very far away from the kinetic time scale you're guessing, but it's the first mathematically rigorous result in this setting where was at least something can be said like for some amount of time that gives this that you can see this wave-Kinetic equation. Okay, but it's still quite far away from conjecture the value of kinetic time scale. Okay, and this is actually the only result that was known like before, like for this particular problem. Okay, so now we're ready to state our main theorem. Our main theorem establishes the wave-Kinetic equation up to time L to the minus epsilon times the kinetic time scale for with tau 0 equals L to minus epsilon for arbitrarily small epsilon. So that can be viewed as we're getting like almost to kinetic time scale, like up to arbitrary small positive loss, up to arbitrarily small positive like polynomial loss, provided that this alpha and L, so as I said, this alpha is the strength of nonlinearity, L is the size of the large box, provided that this alpha and L satisfies some scaling law that is close to either alpha equals L to minus 1 or alpha equals 1. Okay, so as I said, so as I said, so there is we found there is some particular like favorable scaling laws that make the problem perhaps makes the problem behave better. Okay, so this is the statement of the theorem. Fix a positive epsilon, which can be chosen arbitrarily small, and let beta be like arbitrary. Suppose alpha is either comparable to this L to the minus 1 minus epsilon over 2 plus. So here, by the way, this plus means a plus like arbitrary small constant that is like even much smaller compared to epsilon. Okay, so you can think of like a plus something like very small, negligible. Or alpha is comparable to L to minus epsilon plus. Okay, so this is kind of, when epsilon is small, this is close to alpha equals L minus 1. This is close to alpha equals 1. So these are two like favorable scaling laws we're considering. Then as long as t is between L to 0 plus to L to minus epsilon times the kinetic time scale, we would have this ensemble average being the solution to the wave-Kinetic equation plus O of 1 times this t over t kinetic, where O of 1 is a quantity that goes to 0. Actually, in this case, is bounded uniformly by a negative power of L. Okay, so this theorem, and of course, the main point of the theorem is that we can reach the time scale which is arbitrarily close to the kinetic time scale only in this particular scaling laws where alpha equals L minus 1 or alpha equals 1. Okay, so let make a few remarks on this. So before this was the second theorem 2. The theorem 2 like established the wave-Kinetic equation up to some like for other scaling laws, like other scaling laws between alpha and L. we are able to establish wave-Kinetic equation up to some time scale which is much shorter than the kinetic time scale, and this time scale T star actually depends on the scaling relations between alpha and L, and also depend on whether or not beta satisfies genericity condition. Okay, so this is the theorem 2 here. And by the way, these are all joint work with Zaher Hani from Michigan. And this result is supposing alpha and t satisfy these relations. So this relation later on we'll show in terms of a picture, in terms of diagram. If alpha and t satisfy these relations, and also assume that t is less than L to the 2 minus for the arbitrary like torus beta. And if you assume beta satisfies genericity condition, then you can actually get much better, much longer time scale t less than L to d minus. Then the result of theorem 1 holds true for t between L to 0 plus and this capital time t. Okay, so let me make several remarks on the result. So we can so we can visualize these two theorems by doing this log plot, like for alpha and t. We'll view this L as a parameter. You take the log with respect to L, with base L, and then you have this log diagram for alpha and t. This represents like what power of L is alpha and what power of L is t. Okay, so in this picture, if you look at this, this red segment is corresponding to the kinetic time scale t equals alpha minus 2. And actually, so there are natural limitations to the size of t, like in here and here. That's mentioned in theorem 2. But essentially, like the goal of this theory is to justify the kinetic equation like below this red segment, like essentially in this part. Okay, so essentially in this part below this red segment. Okay, and what we have been able to obtain in our theorem is the blue region like below these blue segments. These blue segments represents relation between the alpha and L, say stated in theorem 2, like this like piecewise defined function of alpha in terms of t and t in terms of alpha. And what we are able to do is to justify the wave kinetic equation like for alpha and the t, like it is blue region below these blue segments. And then what is still open in this conjecture is this triangle and these triangles. Okay, so notice that the red and blue segments, they touch exactly at these 2 points 0, 0. And this point 1, 2, and these exactly correspond to the result of theorem 1, where close to these two particular scalings, we're able to get arbitrarily close to the kinetic time scale. Exactly these 2 points where the two lines touch each other. And finally, now actually we can show that there are natural limitations to the kinetic conjecture at t equals L squared in this line for the case of arbitrary tori, arbitrary choices of beta, and that t equals L to d at this line here for if the beta satisfies genericity condition. And these are due to the presence of exact resonances, which we don't have time to talk about, but we just remark that this is the natural limitation that beyond this time, like beyond t equals L to d, we're not really expecting to have the exact like form of the wave equation. We're starting to have something else. Okay, so this is the diagram, and we make a few remarks about the result. First of all, the error term here is O of 1 times T over T kinetic instead of O of 1, and that's because like in the conjecture, the T over T kinetic reaches a size 1, so O of 1 will be small compared to the main term. But in this case, the T over T kinetic is still less than 1, although it's an arbitrary small negative power, but it's still less than 1. And thus we need to compare the error term with the main term, which is the displacement caused by the wave kinetic equation. And since you are evolving wave kinetic equation like up to this short time, the displacement caused by wave kinetic equation would be like essentially comparable to the time. And so in order to justify that our error term is indeed an error term, we need this amount of this estimate on the error term, and this O1 is like a negative power of L. Okay, and second, the result, as I said, the results of theorem 1 and 2 depend on the particular scaling law between alpha and L. In particular, we almost reach the kinetic time scale for scaling laws that are close to alpha equals L minus 1 or alpha equals 1. Okay, so these two particular favorable scaling laws. This can be compared to the kinetic theory where full derivation of Boltzmann equation was done under the so-called Boltzmann-Grad scaling law, while this n times r d minus 1 equals 1, where this n is a number of particles and r is the size of particles. And essentially, like it's so I think the derivation of Boltzmann equation, like for other scaling laws between n and r, is actually not known as of now. Okay, and similarly, like in our case, whether or not we can extend theorem 1 to other scaling laws of alpha is also unknown. Like in other scaling laws, we're only able to obtain theorem 2, which you see that we have these defects that are not really reaching the kinetic time scale. And there's a reason for that. We don't have time to mention, but essentially it has to do with some like certain bad terms where they themselves don't have a good control, but we expect they may have some kind of cancellations, but this is not clear at this point. If they do have cancellation, then we can hope to extend this theorem 1 to other scaling laws. As of now, we don't know. Okay, so finally, we should also mention the recent work of Charles and with Pierre, which Charles actually talked about last week, and they were considering the same problem as us, but on the square torus, where this beta is like a 1 1, each beta j is 1, and they obtained this result getting almost to kinetic timescale, which essentially corresponds to our theorem 1 with the scaling law alpha equals alpha minus 1 minus epsilon over 2 plus. Okay, so the scaling law that's close to alpha equals L minus 1, which is a scaling law corresponding to the point here. Okay, so if you look at the diagram, admissibility diagram we're drawing in the last slide, then their result essentially corresponds to this green region, this rectangle, like below the line, like y equals 2, because I consider the case of square torus, which is not a generic case. And to the right of the line, like x equals 1, that they are essentially getting to this green region, which is a subset of the region we are obtaining. Of course, this is the most important subset because this green region also reaches the point where the red touches the blue, so that this reaches a point where they have this like almost kinetic timescale result. Okay, so this is their result is around the same time as us and independent. Okay, so this is the statement of the description of the results, and let's we have kind of maybe 10 minutes. So I'll briefly discuss the method of proof. It's a little bit technical, but the idea is very simple. So the idea is that we are starting with the Schrodinger equation. So if you remember this Schrodinger's equation, and starting with the Schrodinger equation, we write in the Duhamel form. So this is the initial data, the linear evolution of initial data minus the Duhamel evolution of the nonlinearity. So this is standard in these first equations. We can apply peak iterations, and we write the U formula as a power series. So we have U0, which is a linear evolution, and U1 is a Duhamel like a term. Duhamel term for U0, like for the nonlinearity of U0, the Duhamel evolution of U0 square U0. And if you notice that U0 is if you imagine like the initial data is a Gaussian like is a Gaussian like a function, then U0 is also a Gaussian function, and U1 is a like a trilinear Gaussian function. Is a combination of product of 3 Gaussians, and U2 is if you plug in U2 will be the linear evolution of U0 squared times U1, and also U0 squared times U1 bar. Okay, and U0 will be like a quintilinear Gaussian because it's a product of 5 Gaussians. And then if you write U3, it's like Duhamel evolution of U0 times U1 square plus Duhamel evolution of U0 square times U2 and so on. So this like septic Gaussian and so on. So this is just a standard like a Picard like expansion. And we would like to analyze the terms like that appears in this Picard expansion. So actually, these kind of ideas have been used in the theory of PDEs with random initial data and also stochastic PDEs, and it was like usually referred to as the trick of Bourgain and the part of the bush, where they were going to they were like expanding this solution as a like a random linear term plus perhaps higher terms plus some error term. But the point is that in all these previous results, they have been expanding only to finite, like a small order, like only to the first order, second order. And the reason of that is because when you expand to very high orders, the structure of the solution of these these random terms become extremely complicated, and there is almost an explosive amount of combinatorics you have to deal with. And so because of this, most of the actually all of the results before, they have been restricted to some low order expansions. But here, in order to get to the kinetic timescale, we have to get to like a very high order expansion. And one of the contributions of our work is actually we're able to actually go through these explosive combinatorics, and then we're able to get actually the optimal estimates of each of these terms in the expansion. Okay, so the point here is that these Uj have explicit expressions. As I said, they are like linear, cubic, quintic, septic, like Gaussians, which satisfy pretty nice estimates called large deviation estimates. And their correlations can be easily exactly calculated. The expectation of Gaussians, what they look at, and then you can calculate the correlations. In fact, the correlations between low order terms, they precisely give the nonlinearity of wave kinetic equation. Okay, so essentially the formal derivation of wave kinetic equation, you have, if you attended the Charles lecture last time, you'll see this, like the derivation of wave kinetic equation is exactly by writing out the first like a few terms and calculating these expectations, these correlations, and pass the limits. Okay, so I'll not repeat here, but this is essentially the thing that physicists have done. Okay, so on the other hand, if you consider these are low order terms Uj, the high order terms Uj are actually remainders. In fact, we can prove that this Uj enjoys successively better estimates, namely that the supremum, like if you measure this in L2 norms, measure everything in L2 norms, then these L2 norms decay like rho to J, where rho is some quantity, depends on alpha and t, but in any case, rho is a negative power of L. Okay, so rho is like L to the 0 minus, and so rho to J gets successively better. If J becomes very, very large, and this is like a very, very good term, like with a tiny size in the pseudo norms. And this enables us to perform a fixed point argument in this remainder. Okay, so one question is why, when do you expect this estimate to be successfully better? Why do you expect this to be successfully better? So let's look at so we'll perform a heuristic argument here. Let's look at the initial data U0, which we can normalize to have a unit size, and we look at the second iteration U1. And then if we calculate the expectation, we calculate the size of U1, then essentially you are having these factors, and then U1 is a Duhamel evolution. So this is a cubic nonlinearity, the cubic product of these random variables. And then you have this Duhamel evolution, which gains you this 1 over omega being the resonance factor. And then in the end, you can get this factor, this integrating time being the minimum of t and 1 over omega. And then, for example, without loss of generality, you can restrict to the omega being less than 1 over t, where omega is the resonance factor that is shown here, which essentially you can think of as the factor quantifying whether you are close or far away from resonance. And here we are assuming that in this term of concern, we're assuming that we are close to resonance. Okay, and then you are considering these sums over the K1, K2, K3 of these products of these cubic Gaussians. And then what happens here is that if we remove the degenerate contribution by the so-called weak order, which has some technical details that we will omit, then the rest of this sum will enjoy the square root cancellation. And that's the main point of this randomness, because if you consider a sum of this eta j, each eta j has size 1, but if you sum over them, then they will get a square root cancellation that the generic size of this sum would not be the number of terms involved, but the square root of the number of terms involved. And that is consistent with, for example, the central limit theorem, where you have a sum of IID random variables, xj, then the sum of xj is not comparable to the number of terms in the summation, but they're comparable to the square root of number of terms in the summation. And that is the square root cancellation, which is a very typical thing in all these random data theorems. Okay, so it's compared to central limit theorem. And then, of course, we may do some normalizations to restrict the number of k's. And by dimension counting argument, the number of terms in the sum will be like this. Okay, so by the way, like this is not very precise in the setting. In some setting, we only get weaker result, which is ultimately the reason why we don't get optimal results in the general between the general scalings between alpha and L. But that is a heuristic. That's something you would expect. Okay, then if we calculate the second iteration, then the size of second iteration will be this, this factor here times the number of terms to the square root of number of terms, which is this one. Then you see, like, if in order for this to be less than 1, you can calculate if this happens, if mod t is less than L to 2D lambda minus 4, which is the kinetic timescale. So that's to say this kinetic timescale emerges like naturally from these heuristic arguments about these randomized Gaussians. And these heuristic arguments, where the crucial thing is to exploit this square root cancellation, it actually effectively changes the scaling of this problem. And this new scaling, if you consider the traditional deterministic scaling, you won't be able to get to this kinetic timescale. You're essentially getting to the timescale in deterministic setting in the work done by Buckmaster, Zaher Hani, and Shatat. But the randomness actually brings a different scaling to this problem, and this scaling we're going to call them the probabilistic scaling. So I have a recent work with Namod and Yue, which was supposedly last December, where we also introduced this notion of probabilistic scaling. We're studying the low regularity almost sure Walpolson's problem for Schrodinger equations, especially considering the Walpolson problem at the Gibbs measure regularity, which is a very subcritical with respect to the usual scaling, but it's supercritical with respect to the usual scaling, but subcritical with respect to the probabilistic scaling. And this notion of probabilistic scaling is exactly coincides with the prediction, with the calculation here that predicts the kinetic timescale. Okay, so see that these two questions, this weak turbulence question and the random data, almost sure local Walpolson problem, they're actually closely related. Actually, there is a much closer relation that cannot have time to talk about here, but there is a much closer relation between these two, that these two equations, you can essentially view them as a kind of parallel questions each other. And then, of course, this exhibits also probabilistic scaling that we introduced in this other work. Okay, so we probably don't have much time, so I'll just very briefly go over the proof. The proof is we do this expansion, this high order expansion, where each UJs are the multilinear Gaussians plus the error term W, and we prove successfully better bounds for these UJs, which has a explosive amount of commentaries that we're able to go through that. And then we perform a fixed argument for W, which W is in very nice space with a very tiny norm we're looking at. So this is not hard, but then in the end we'll need some kind of estimate for random matrices that also Charles mentioned in his talk. And then we calculate the correlations between these multilinear Gaussian terms, which is not very hard because high order terms are error terms and low order terms are the main terms, which are easy to calculate. And exactly these low order terms give the nonlinearity in the wave equation. The high order terms are error terms that can be neglected when L goes infinity. And finally, we apply this number theoretic method to justify the passage from the discrete sum to the continuous integration. Okay, so we'll focus on the steps 2 and 3, where essentially, I think I'll just mention one thing, that these the kind of commentaries involved in these UJs are essentially the commentaries associated with so-called ternary trees, which you can view as a version of the Feynman diagrams that Charles mentioned last time. Okay, so then you see this is the T is like ternary trees, and then you look at this. you look at this, so you have some terms associated with that, and then you see here the representative the representative term of the ternary tree is that you have k, which is output like a frequency, and this has to do with the frequency k1, k6, k2. It's because this u is this term is a Duhamel evolution of a cubic term. The output frequency is k, and the frequencies in cubic terms are k1, k6, k2. And then the K6 here has no more structure. So K6 is corresponding to a linear evolution, the first iteration, linear evolution U0. And this K1 has again 3 children, which means that there's 3 subsequent frequencies. K1 is a combination of K3 minus K4 plus K5. And so K1, this term, this corresponding input would be one of the cubic evolutions of the 3 linear inputs, and this is 3 cubic evolution of 3 linear inputs. So this ternary tree would correspond to a static term where you start with 3 linear inputs to produce a cubic term. You have another 3 inputs, linear inputs, produce a cubic term, and you put this cubic term, and the linear input, you put it together to produce a static term, like via the iteration Pika iteration scheme, okay, via this Pika iteration scheme. Okay, so these kind of terms that are associated with ternary trees, and then you have to, to estimate this term, you have to perform like a counting estimate associated with ternary trees. And actually, we also need to consider the pairings between ternary trees, which don't have time to talk about, and then in the end you're reduced to like a counting problem, like for ternary trees, and then this counting problem is actually the main thing of the work that we're able to develop like a optimal way of doing these counting problems for ternary trees. And then once you have, and then this eventually will lead to the bound for the higher order Gaussian terms. And once we have the bounds for higher order Gaussian term, the next thing is to perform a fixed point argument for the remainder term W. And this essentially, you can see that the most important thing is a linear term in W, and the linear term you have to show that it satisfies like L to L2 like a bound like being a negative power, and this is here we're doing it by higher order T star argument. Actually, we're having a result we didn't write in this paper, but having a result that is a fairly general result that concerns the L to L2 bound of a random matrix with arbitrary like coefficients, and this result actually, if we apply this result, we can easily get to the bound for this one. But although we're not writing this result now in this paper, we're perhaps writing this result in a future paper. But this essentially like down to earth. This is like it's obtained by using this higher order T star method. But actually, we are going to have a very nice like general results that can be used as black box. But we'll do this. We'll write this in a future paper, not in this one. Okay, and this T star argument, the last piece of the T star argument, we are going to. So here, this is kind of like this linear operator is you start from W, you multiply this tree term UT2, this tree term UT1, and when you iterate, and that's essentially corresponds to this tree structure. You start from this node which represents W, you add in T1, add in T2, and then you take the conjugate, you add in T2, add in T1, add in T1, add in T2, add in T2, add in T1, you obtain these this big composite tree. And then it turns out that this big composite tree is no different from any of the previous ternary trees we have been discussing, and then they satisfy the same estimates, and these estimates they can turn into, in the end, they can turn into the estimates for the kernels for this LL star, and this eventually leads to the operator norm bound for L. And then with this, we're able to get to the fixed point argument for W, and then we get this control for the solution. Actually, you have seen here that solution is like the linear Gaussian plus cubic Gaussian that is smaller, plus a quintic Gaussian that is even smaller in size, plus these high order expansions. But essentially, they satisfy kind of the nice estimates as usual Gaussian does, and the correlations they actually also go to 0 when L goes to 50. Okay, so I guess I'll just stop here, and thank you for